Hello, this is Mrs. Brookshire. We are working on the last section of notes in chapter 4, and it is section 4.2, part 3, designing experiments. So a little bit more with experiments. I've got some vocab ready for you to look at, so you can stop the video. I'm going to kind of read through these, and then we're going to go through a bunch of examples. So the first word we've talked about a little bit already is control. In an experiment, control means keeping other variables constant for all experimental units. So you want to have a control so that you can actually, see that the treatments you're imposing are actually making a change in something. All right. Replication. In an experiment, replication means using enough experimental units so that a difference in the effects of the treatments can be distinguished from chance variation due to the random assignment. There must be at least 2 experimental units receiving each treatment to achieve replication. So replication is an important thing in an experiment as well. And then we're going to go through the 4 principles of experimental design. 1, comparison, which I believe is misspelled. Sorry about that. I got an extra S. Using a design that compares 2 or more treatments. Okay. So we have comparison. We've got to have random assignment. Use chance to assign experimental units to treatments. Doing so helps create roughly equivalent groups of experimental units by balancing the effects of other variables among the treatment groups. You've got to have control. Keep some variables the same for all groups, especially variables that are likely to affect the response variable. Control helps avoid confounding and reduces variability in the response variable. And then the last one, which we just talked about, was replication. Given each treatment to enough experimental units so that the differences in the effects of the treatments can be distinguished from chance differences between the groups. All right, so we're going to go over, so stop this if you need to, copy, or go take a look at your filled in notes. The first problem we're going to go through, does regularly, you've heard this before, probably, taking aspirin help protect people against heart attacks? The Physician's Health Study was a medical experiment that helped answer this question. In fact, the Physician's Health Study looked at the effects of 2 drugs, aspirin and beta-carotene. Researchers wondered if beta-carotene would help prevent some form of cancer. The subjects in this experiment were 21,996 male physicians. There were 2 explanatory variables, factors, each having 2 levels. So aspirin, yes or no if they took it, and beta-carotene, yes or no. Combinations of the levels of these factors form the 4 treatments shown in the diagram. 1/4 of the subjects were assigned at random to each of these treatments. So you've got yes, aspirin. You can kind of look through here. So these were the 4 treatments. On odd numbered days, the subjects took either a tablet that contained aspirin or a placebo that looked and tasted like the aspirin but had no active ingredients. On even numbered days, they took either a capsule containing beta-carotene or a placebo. There were several response variables. The study looked for heart attack, several kinds of cancer, and other medical outcomes. After several years, 239 of the placebo group but only 139 of the aspirin group had suffered heart attacks. The difference is large enough to give good evidence that taking aspirin does reduce heart attacks. It did not appear, however, that the beta-carotene had any effect on preventing cancer. Okay, so we're going to answer some questions. I've kind of gone through. We'll talk about the answer, and then you can kind of jot down what we talk about. Explain how this experiment used comparison. Okay, well, researchers used a design that compared each of the active treatments to a placebo. So that's how comparison was used in this experiment. Researchers used a design that compared each of the active treatments to a placebo. Okay. Part B, explain the purpose of random assignment, randomly assigning the physicians to the 4 treatments. Okay, so the purpose of it was so that you could see if it was actually, it says random assignment helped ensure that the 4 groups of physicians were roughly equivalent at the beginning of the experiment. So that's why you want to have random assignment, so that you can assure that you have equal numbers, roughly equivalent, at the beginning of the experiment. So they did say they divided them up into the 4 different groups. Okay, part C, name 2 variables that were controlled in this experiment and why it was beneficial to control these variables. So the experiment used subjects of the same gender and the same occupation. Using only males reduces variability in response variables. The other thing I think was with the physicians, maybe they have the same stress level. So those were 2 variables that were controlled in the experiment. And, just using the same gender and same occupation kind of reduces variability due to other aspects. Explain how this experiment used replication. What's the purpose of replication in this context? There were over 5,000 subjects in each treatment group. So that ensures that, we kind of ran out of room here. So there were over 5,000 subjects in each treatment group. It ensures that heart attacks were due to aspirin, not chance variation. So I'll give you a second. There were over 5,000 subjects in each treatment group. It ensures in heart attacks were due to, I just kind of jumped up here to the next page, due to aspirin and not chance variation. So that is how replication was used, and that was the purpose of the replication. Okay, so what we did here is we kind of went through all the principles of, we included the 4 principles of experimental design in this one problem. Okay, so the next question or next problem we're going to work through. Many utility companies have introduced programs to encourage energy consumption, conservation among the customers. An electric company considers placing small digital displays in the households to show current electricity use and what the cost would be if this continued for a month. Will the displays reduce electricity use? One cheaper approach is to give customers a chart and information about monitoring their electricity use from their outside meter. Would this method work almost as well? The company decides to conduct an experiment using 60 households to compare these 2 approaches. So either the display or they keep their chart, with a group of customers who receive information about energy consumption but no help in monitoring electricity use. Explain why it's important to have a control group that didn't get the display or the chart. Describe how to randomly assign the treatments to 60 households. And what is the purpose of randomly assigning treatments in this context? Okay, so why would we want to have a control group? Let's think about that first. Really, you want to have a control group so you have a baseline to determine how much less electricity is used in each treatment group. That's basically going to be the explanation every time you have a control group. So let's write the control group. Control group would give a baseline. Would give a baseline to determine how much less electricity, is used in each treatment group. That's basically the purpose of any control group. Okay, it's just like as a baseline to actually compare to see if there are, any differences. All right, number 2, describe how to randomly assign the treatments to the 60 households. The easiest way, anytime you do a random assignment, is numbers and a hat. And honestly, if you're asked to describe a way to do a random assignment, that's what I would do. I mean, I know it kind of seems like, oh, you always do the same thing, but like if you use the random digits table, which is also another way you could do it, and you guys could think of other ways, but I'm going to go with the slips of paper. Okay, so number houses from 1 to 60, and write 1 to 60 on slips of paper. Put numbers in a container. Whoops, put numbers in a container. Mix well. Draw out 20 slips of paper without replacement. Draw 20 slips with no replacement. And we'll just say those households receive a display. And then draw out another 20 slips of paper. Those households receive a chart. Draw another 20 slips of paper. Those households receive a chart, the chart. The remaining 20 households will only receive information about energy consumption. The remaining 20 households will only receive information about energy consumption. Info about energy consumption. And then number 3, what is the purpose of randomly assigning treatments? I mean, obviously to create household groups that are equivalent. Random assignment creates groups, household groups that are equivalent. Household groups that are equivalent. This ensures that effects of the other variables are spread evenly among the 3 groups. Okay, so this ensures that effects of other variables are spread evenly among the 3 groups. So any other, it would be in every group, evenly among 3 groups. So if there were any other outside variables. Okay? Okay, so example of a completely randomized design. This is not a required feature on the AP exam, but a very good idea to support your explanation. So you have 20 volunteer students. You are going to do a random assignment to break them up into 2 groups. So you're going to have group 1 with 10 students, group 2 with 10 students. And then you will have, this one receives treatment 1. This was, I think, the caffeine problem. With caffeine, and treatment 2, no caffeine. And then you compare the change in pulse rates. So that's the caffeine one that we did in the last video. Okay, so this is an example of completely randomized, but it's a very good way to explain your, like, how you're going about it. Okay, so Next problem, concussion-related measures improved in high school football players who drank new chocolate milk, announced a recent headline. In the study, researchers compared a group of concussed football players given a new type of chocolate milk with a group of concussed football players who received no treatment. Explain why it isn't reasonable to conclude that the new type of chocolate milk is effective for treating high school football players with concussions based on this study. Okay, so think about why, you've got the situation and why that would be reasonable to conclude that it's effective for treating high school, why it isn't reasonable to conclude that. So if you think about it, it's going to talk about how we can make this a better design. So what I had said, and I'm going to kind of let you kind of follow along here as I write this, is it is possible that the group who received the new chocolate milk improved because they were being treated and expected to get better, not because of the new chocolate milk. So it's possible the group treated or the group given new chocolate milk improved because they were being treated and expected to get better. And expected to get better. Not because of the new chocolate milk. Not because of the new chocolate milk. All right, part B. To test the effectiveness of the new chocolate milk, you recruit 50 high school players who suffered a concussion in the previous 24 hours to participate in an experiment. Write a few sentences describing a completely randomized design for this experiment. So you would want to do a completely randomized design. So what could you do? You could number players from 1 to 50. Number players from 1 to 50. Use a random generator to generate 25 integers, because you want to cut it in half from 1 to 50. Give them new chocolate milk. And then regular chocolate milk to other players. Regular chocolate milk to others. Regular chocolate milk to other 25. And then you want to compare, obviously. Okay, so that's how you want to kind of talk about how would you make it completely randomized. That's what you could do. Okay, so we're going to talk about block and randomized block. Okay, so a block is a group of experimental units that are known before the experiment to have something similar. So when you block something, you want to put them in groups because there's something similar in some way that is expected to affect the response to the treatments. In a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. So let's kind of look at this diagram, and I think it explains it pretty well. So you assign the blocks. So you've got these volunteers, and this was about a smartphone. So the question is, so you've got 10 volunteers, okay? 4 of them have a smartphone and they know how to use it, and then 6 of them, they don't have a smartphone, so they're not sure how to use it. So this is how we blocked these, whether they were smartphone users or non-smartphone users. So that would be your blocking. And then within those groups, you're going to do random assignments and then compare. And then here, this group, you'll do random assignment and then compare. And so the random assignment was, they just divided those in half, and then compared. So this one used keyboard A, this one used keyboard B. It was 2 different keyboards I think they were trying to compare. So that was mainly what you were trying to do, is compare which keyboard was better. That was the problem. And then you compare these 2, and then you compare those results. So when you make an experiment and you're doing it by blocking means that you are, you're separating them by some likeness, okay? And then randomized block means, okay, once you get those separated, then you're going to randomly assign them the treatments. So this is an outline of a randomized block design for a smartphone experiment. The blocks consisted of volunteers who have used smartphones and volunteers who have not used smartphones. The treatments are keyboard A and keyboard B. All right, so don't mix the language of experiments and the language of sample surveys or other observational studies. You will lose credit for saying things like you used a randomized block design to select the sample for this survey, or this experiment suffers from non-response because some subjects dropped out during the study. So don't be mixing those 2 things up, okay? So the block design, a lot of people kind of say, it kind of reminds them, if you think about when we did a survey though, it reminds them of the stratified in a way, because you're dividing up by likeness. So don't use that anywhere, but it's kind of the same idea, but for an experiment, okay? All right, so here is the problem. A popcorn lover wants to determine if it is better to use the popcorn button on her microwave oven or to use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. To obtain the experimental unit, she goes to the store and she buys 10 bags of 4 different varieties of microwave popcorn. You got butter, cheese, natural, kettle, for a total of 40 bags. Describe a randomized block design for this experiment. Justify your why you are blocking in that way. And then we're going to explain why a randomized block design might be preferable to a completely randomized design for this experiment. Okay, so you want to form your blocks based on variety. So you have 20, let's see, how many did she buy? 40 bags. Okay, form blocks based on variety is what we're going to do. Form blocks based on variety. Okay, so that's how we're going to block. Randomly assign 5 bags of each variety to popcorn button and treatment, and 5 to just timed to the popcorn button, and then the other 5 to timed treatment. Okay, so we're going to randomly assign 5 bags of each to popcorn button and 5 bags to time button. Okay, so then you would place the 10 same variety bags in a box, and then pick out 5 bags in a box. Pick 5 bags. That would be the popcorn button treatment. Okay, and then the other 5 bags would be the instruction on the bag. Other 5 instruction on bag. Repeat this process for the other 3 varieties. Repeat this for other 3 varieties. After popping all 40 bags, count unpopped kernels and compare results. Kernels and compare results from the 4 varieties. Okay. So, one thing I was going to say is you can write this out in paragraph form. Another thing you could do, another way you could express this is if you could actually make a chart like this. So you would have, like, if you did the chart, I kind of like the chart. You would start off with your 40, I keep looking. Okay, yeah, 40 bags. So we have 40 bags of popcorn, and we'll have your, 4 groups. So you've got your, whatever the 4 choices were. What did you have? You had, the different varieties were butter, cheese. So that was 10. Cheese, 10. Natural, 10. Kettle, 10. Kettle corn. And then you would randomly divide those up. You would have the timed and the directions for each of those. So there'd be 5 here, 5 here. You would divide those up the same way. And then you would compare these, and then you would at the end compare. So you'd have to write that all the way out. But that's kind of a cool way to do that. Okay, so the next question was, explain why a randomized block design might be preferable to a completely randomized design for this experiment. Okay, so a completely randomized design means you wouldn't block at all. So randomized block design, I'm just going to abbreviate here, accounts for variability, created by the different varieties of popcorns. Created by the different varieties of popcorn. So this makes it easier to determine if using the microwave button is more for reducing the number of unpopped kernels. So that's important here, I think, because, they may, depending on it, like if it's butter, it might be, more congealed or harder to pop. So you definitely want to, on this one, use the block design to compare this. So that experiment, that would be the best way to do this one. Okay. And then the last thing we're going to discuss today, and most of this I've just written out, so it's getting long here. So we're going to just kind of talk about what matched pairs is. So a matched pair design is a common experimental design for comparing 2 treatments that uses blocks of size 2 in some matched pairs design. 2 very similar experimental units are paired, and then the 2 treatments are randomly assigned within the pair in others. Each experimental unit receives both treatments in a random order. So what you're going to do, this is all a matched pair, think about that, is comparing 2 treatments using blocks of 2. So you match up these pairs with each other, and then you would actually give the treatment to both in different random orders. So we're going to look at an example. A consumer organization wants to know if using a certain fuel additive increases the fuel efficiency in miles per gallon of cars. A total of 20 cars of different types are available for testing. Design an experiment that uses a matched pairs design to investigate this question. Explain your method of pairing. Okay, so what I said is give each car both treatments. So you're going to have 2 cars using each car as its own pair. Oh, okay. So give each car both treatments. So you can do it this way too. Like you have a car, you're going to give it both treatments, and it accounts for the variation in fuel efficiency. For each car, randomly assign the order in which treatments are assigned by flipping a coin. Heads, use additive first, no additive second. Tails, no additive first, and then use additive second. For each car, record the fuel efficiency after each treatment. So one way you could do it is like count each car, take each car and use each car as its own pair. So then this is going to account for variation in fuel efficiency, which makes sense because it's like looking at the same car, put it in, what was the gas mileage, and then don't put it in the next week and see what happens. So that's one way. And then we're going to kind of just, and I'll let you guys just sort of, this is getting a little bit long, so I'm going to let you guys kind of stop and copy, or we'll just kind of talk through it and you can go and copy the notes. Okay, researchers would like to design an experiment to compare the effectiveness of 3 different advertisements for a new television series featuring the works of Jane Austen. There are 300 volunteers available for the experiment. Number 1, describe a completely randomized design to compare the effectiveness. So completely randomized, don't block it all, just do a randomized design. Number of volunteers, 1 to 300, use a random number generator. The first 100, watch the first advertisement. The second 100, watch the second advertisement. The remaining 100, watch the third advertisement. Compare the differences of the 3 groups. So that would be completely randomized. Number 2, describe a randomized block design for this experiment. So how could you block these people? One thing would be to block them by how familiar they are with Jane Austen. So you would get volunteers in each block would be randomly assigned to one of 3 treatment groups. So what you could do is you could say, are you familiar with Jane Austen's work? Are you not? So that could be your 2 blocks. And then once you get your 2 blocks, divide those up into a third of those get the first, a third the second, a third the third. And then after viewing the advertisements, research would gauge effectiveness. So that would be block design. And then why might a randomized block design be preferable in this context? Like why would this be better than, why would 2 be better than 1? Because it accounts for the variability and effectiveness due to being familiar with Jane Austen's works. It makes it easier to determine the effectiveness of the 3 different advertisements. So that is just a really good summary problem on regular, just a completely randomized design versus a block design. And we are done. So if you need to go back, look at your, pause this, rewind, or go look at your filled in notes. And we are done with chapter 4 at this point. Talk to you later. Bye.